So, we were talking about EOF by the Nordist-Planck model for fully developed Navier-Stokes Nordist-Planck equation and fully developed EOF in a slit microchannel. Now, we have derived the equations. Now, this dimensional analysis is we have to perform now. Now, what is the importance of dimension analysis and similarity is a little bit described over here. Now, see, the dimensional analysis, basically what we do is a grouping of some parameters. There are individual parameters. So, these individual parameters, instead of that, we group to a single, sometimes a non-dimensional parameter, so which characterize the flow or the electroosmotic flow or electrokinetic transport for this situation. Now, for example, in the hydrodynamics, we have the Reynolds number, well-known Reynolds number. So, similarly, for the electrokinetics, the most commonly used are the Reynolds number, Debye-Huckel parameter, Zeta potential, Schmidt number, and Peclet number, etc. Now, for that, through these parameter values, we can have a correspondence between two phenomena in a similar configuration. So, that is the importance of the dimensional analysis. Now, in previous class, we have derived the Nordist-Planck model for fully developed EOF, where the velocity, which is parallel flow we are considering, this is u is along the axis of the channel or along which the electric field is applied, and this is the distribution of the ions. So, we have taken monovalent binary ions. So, G and F are the concentration of the ions. So, this satisfies the set of equations, ordinary differential equation for that matter, and along with these boundary conditions are governed by this way. So, as we stated before, your boundaries are y equal to 0 and y equal to 1. These are the y equal to 0 is the lower wall, y equal to 1 is the upper wall. So, on the wall we have 0 fluid velocity, 0 normal flux. So, normal flux condition given by this way, along with either constant zeta potential or you can have a constant surface charge density. Here kappa is the Debye layer, inverse of the Debye layer thickness. Now, what we did is in deriving this equation, we have non-dimensionalized the velocity by this capital U, which is similar to the Smolchowski velocity, Helmholtz-Smolchowski velocity, but potential is the phi 0, which is the scale for the electric potential, and E 0 is the applied electric field, and phi is scaled by phi 0, the thermal potential RT by F, which is about 0.02 or or you can say 26 millivolts or 0.026 volt, and y we have scaled by the height of the channel, and the surface charge density is normally scaled by this epsilon E kappa phi 0. Now, if you look at this equation, so and the governing equation, what you find that these equations are governed by the parameter kappa h and the zeta potential or the surface charge density parameter sigma s. So, individually we did not have to specify the height of the channel or the diffusivity, because here these are the convective transport of ions are all neglected, and also the convection terms in the fluid flow equation is also neglected. So, this is simply governed by the kappa h. So, if I prescribe the kappa, and the kappa means the Debye layer thickness, again the Debye layer thickness is also governed by the electrolyte concentration and the permittivity of the electrolyte and so on. which has already been defined before. So, and other things like temperature and real gas constant, it has a constant value. But to fluid, you can have a different viscosity, different permittivity. So these parameters are all grouped together to form this kappa h, and this is u, the small Chomsky velocity. Now, if you look into this equation, what we find that if kappa h is very large, so kappa h large means the h by lambda is large, h by lambda is large. In other words, the d by length is very small, lambda is small. So in that case, what we find that g minus f is occurring. So that means outside the code of the channel, we can have a electroneutrality of the solution. And also these two equations, the u and phi equations, have the same form, but they have a different boundary conditions. So, but if I choose the boundary condition as phi equal to zeta, and see, the one main thing is that for the electric potential, only the gradient is important. So even if I define, say, some phi minus zeta, and I can assume phi equal to 0 on both the wall. So this form of the phi won't change, because it satisfies the same equation if I redefine phi as phi minus zeta. So u and phi have the same solution, provided you have phi equal to 0 if I consider. But if I choose kappa h is of order 1, so that means if lambda, the d by length is not very thin, so in that case we can have g minus f to be non-zero. Now, one way is to solve this set of equations, which is strictly speaking is a nonlinear boundary value problem, because you have the 2-point boundaries, y equal to 0 and 1. So one can compute this, solve this one. But one easy way is that we can have a integral, a two integral for the Nares-Planck equation for this one dimension case can be solved for a form like this, where if we consider this subscript 0 a reference point outside the Debye layer. So these two integrals satisfy the equations for g and f. Now the gradient of phi is important, so I can redefine the induced electric potential in this case as phi minus phi 0. So if I do that, I can get g equal to g0 e to the power minus f and f equal to f0 e to the power phi. Now these two shows that they are independent of kappa h. So whatever the choice of kappa h, the ionic concentration is invariant. Okay, and it is a somewhat similar to the Boltzmann distribution also. Now I can choose that if we have a situation that outside the Debye layer you have a electroneutrality, the reference point if I choose in such a way that electroneutrality has occurred. So in that case I can have the f0 equal to g0, which is basically the mole fractions. So at the equilibrium or in the core where there is a electroneutrality is established, so I can write the solution as g equal to e to the power minus phi and f equal to e to the power phi. This scaled, of course, these two. These are the two other mole fractions of the cations and anions. So clearly these are governed by the same as the Boltzmann distribution of ions. So and also they form the solution of the Nares-Planck equation. So for this fully developed case, what we can say is the convective transport has no effect if we have a core neutrality is established. So the Debye length, of course, here say always we mention about the high Debye, large Debye length, thick Debye length, thin Debye length. So when we say the thin Debye length, so we have to understand that it is a highly concentration of the electrolyte is high, and if it is a thick Debye length, so we can that implies that the concentration of electrolyte is low. So now if we make a obtain the solution for this Nernst-Planck equation, and now we compare with the Debye-Huckel solution which was obtained before. So we get a situation, a form like this. So if the Debye-Huckel solutions and the Nernst-Planck solutions, whichever is obtained, if we make a comparison with these two, so we get a comparison of this form. Now what we find is that when the kappa h is quite low, so in that case we find a situation where there is a difference in the solution. See here, for the sake of comparison, we have taken 0 to 1. 0 is the symmetry line. Of course, when we are solving the Nernst-Planck equation, we have not imposed any symmetry. What we have done is here that we have taken -1 to 1 as the domain. So that means the walls are at -1 and 1, and so 0 is the symmetry line on the channel, and that is how the Debye-Huckel solution is obtained. So what we find that Debye-Huckel solutions are okay at thinner Debye length. So that means when electrolyte concentration is high, kappa h are say greater than 1, so we get a good comparison with the Debye-Huckel solution. But if we have the Debye layer thickness are comparable with the channel height, so that means the lambda k h equal to 1 means lambda equal to h. So in this case, basically what is happening is the overlap of Debye layer. So h is the half height of the channel. So that means the Debye layer, what is occurring on the upper wall, adjacent wall, so they are overlapping. So there we may not have a electroneutrality of the within the code itself. So that is expected. So that's why we have a slight difference from the Nernst-Planck computed solution and the Debye-Huckel solution. Another thing is that interesting thing here, you see when kappa h is large, we get a plug-like type. So that means there is within the code of the channel, we have a constant velocity, and constant velocity is nothing but the Smolchowski velocity. Here, of course, zeta potential is taken to be -1, which is equal to zeta potential -1 means it is scaled by phi 0 thermal potential. So this is the same as the Smolchowski velocity, which should be at 1, and this is the fluid property. Now we see the distribution of mole fraction. Now what we find that when kappa h is large, kappa h is 1, so these are the 2 mole fractions. So that means in the code there is a g minus f is non-zero. Now charge density at any point within the fluid is proportional to g minus f, because that is the net amount of concentration of the ions. So if g minus f is non-zero, so that means the fluid is electrically non-neutral. So what I find is kappa h, when it is a small value, so we get a g minus f is non-zero, whereas in this situation, so where kappa h is large, so that means the Debye length is thin or electrolyte concentration is high, what we find that G and F curves are coinciding with each other. So that means you have a 0 charge density in the code is established. Only a little bit jump is there or difference is there near the wall or near the Debye layer. So this is y equal to 1 is the wall over which the Debye layer forms. So close to the Debye layer, you have a large value of G minus F. Outside the Debye layer, you have a 0 charge density. So and also the ion distribution is not very much perturbed, because ion distribution is not affected by the fluid convection, the solution whatever we have shown. Of course, here we have taken a Debye-Huckel approximation, so that way the phi whatever is obtained is not the same as the Poisson-Boltzmann case. Now, if I compare with the, instead of Debye-Huckel approximation, if I take the full Poisson-Boltzmann equation, that is the nonlinear Poisson-Boltzmann equation for the electric field, and if we compute that nonlinear equation and compare with this solution of the differential boundary value problem we have described, that is what we referred as the Nernst-Planck model or the NP model. So, what I find that it is just the same, they are just coinciding with each other. So, there is even see the Debye length is lambda 0.8. So, where the channel height is 20 nanometer. So, 0.8 nanometer. So, this is the 0.8 nanometer, we find the constant core flow, that means within the core y 0 and 1 are the bound 0 and 2 are the two boundaries here. So, outside the Debye layer, fluid is quickly approaching the small Chomsky velocity. Again, here zeta is minus 25, should be minus 1. This is in dimensional form, should 25 millivolt, which is nothing but the thermal potential. So, we get a value as saturation value as 1, or the constant core velocity. But when I increase the lambda, thickness of the Debye layer is increasing. In other words, the electrolyte concentration is reducing. We find a situation is a parabolic flow type of parabolic curve, like a Poisson flow is establishing between the two parallel plate channels. We get a situation, this flow resembles to the parabolic profile which appears in the Poisson flow. Actually, these are the characteristics, that plug-like profile. It is very important in many microfluidic devices. And also, what we can see is that we can regulate the flow, because UHS is just a linear function of E0, that external applied electric field. Another thing, as we discussed few slides, that you see the code neutrality is not established when lambda is large, lambda equal to 8 or 4 nanometer, say 8 nanometer, you get the G and F profile are given by these two curves. So, obviously, G minus F is non-zero within the core, but as we increase the electrolyte concentration or decrease the thickness of the Debye layer, so what I find is that the code neutrality is establishing. That means G minus F is becoming 0. Now, current density can be obtained, as we discussed before also for the Poisson-Boltzmann model. The same way, the current density, this vector is given by this way. So, if I take this characteristic current density as I0, which scales that I. So, now this portion is becoming a non-dimensional, because we have scaled by the non-dimensionalized the variables. Here Q is the velocity we have considered. Now, Q is the fluid velocity and Xi is the mole fractions, all this. Now, we have introduced one parameter here. This is the Peclet number. Now, Peclet number appears which we have not defined before. So, Peclet numbers appears because of the diffusivity of the ions and the fluid velocity. So, basically the Peclet number, which is governed by the, say if I write the PE is Reynolds number into Smith number. Now, what is Smith number is, so if what is that Reynolds number? We have, this is basically here is the u0 is the velocity, and this is the length scale h, and this is the nu, which is the kinematic viscosity, and Smith number is nothing but nu by di, where di is the molecular diffusivity of the ion. So, here we have taken the di to be SEM if we consider the binary electrolyte, and if I consider dr equal to d2 equal to d, there is the diffusivity of all the ions are same. So, in that case we find that this number, this non-dimensional number, Peclet number, becomes u0 h by di. So, this is basically the ratio of the advective transport of the ion by the molecular diffusion transport. So, this is the Peclet number occurs. Now, in electroosmotic flow, one thing to remember is that this quantity, that this non-dimensional parameter Reynolds number is quite small, because h is very small in the micrometer range, u0 is also small, but this can be quite large, because di is normally very small for the biocolloids, biofluids and all. So, di is like 10 to the minus 10 or minus 9 factor. So, in that way this product RDSC can be of order 1. So, if RDSC, this Peclet number, is neglected, so this contribution of this term has no use. So, basically the ion density, which is governed by the concentration of the concentration gradient, and this is the mobility of the ions. Of course, we have not dimensionalized this equation, we have derived before, and the convective transport of the ions. Now, this term can be 0, this last term, provided you have a 0 electroneutrality or the Peclet number is very small. Now, through the Nernst-Planck solution, whatever the equations we have solved, so we define this Ix as the cross-sectional average current density. Now, here we have, what we have done is a combined flow of electroosmotic and pressure driven flow. So, that means there is a constant pressure gradient is also applied along the axis of the channel, which is measured by this non-dimensional factor g. So, now if we compute, or if you plot the average cross-sectional average current density, here it is written in dimensional form, Ampere per meter square against the voltage or electric field, voltage drop or electric field. So, what I find that, so let us first follow the case g equal to 0. So, that means pure electroosmotic flow. So, you get a linear variation. So, this linear variation suggests that it is that convective transport have very little effect, and also it further shows that if I vary this g, that means the pressure difference, there is no change. Now, here we have taken the Debye length as 4 nanometer and 2h is 100 nanometer. So, they are far apart. So, that means a core neutrality is established. So, this we may have this Zixi, sigma Zixi is 0 within the core. So, we get a linear solution. But if we have lambda large 40 nanometer, so here there may have the core of the channel may be electrically neutral. So, we find that the effect of G. The effect of G is now quite evident from here, a linear increment in the current density. So, this is how we can measure the electroosmotic pump and current density through a slit channel on fully developed EOF. Now, another important aspect in electroosmotic flow is the solute transfer. So, that means the microchannels are connected to reservoirs. So, what we need is transferring the solute from one reservoir to the other. So, the solute can be a neutral solute, that means electrically neutral, or a in trace concentration. Trace concentration means its concentration is too low that it does not change the electric activity of the or electrokinetics of the buffered electrolyte. So, if we consider the solute concentration is very low, so which is referred as the this trace concentration. So, the other properties of the electrolyte are independent of the presence of solute. Now, the solute transport equation are governed by this advection diffusion, and if it is a charge, so there will be a electromigration. So, these equations, advection diffusion and electromigration, as we have described before. So, this is the one, the Peclet number, which we just defined before, and ds is the molecular diffusivity of the solute. Now, this Q, this is the can be a combination of the, if it is a neutral solute, so we do not have this second term, so it is transporting with the or advection velocity is nothing but the fluid velocity, background electrolyte velocity. So, we have the advective velocity as Q equal to U plus omega s E. Omega s is the mobility of the analyte ionic species if we consider a charged solute. So, the solute transport equation and so is governed by this equation. So, if I take this is out, Ws is omega s is 0. So, what we find that if I know the value of u at every point, we know the solution u, one can solve the this equation, advection diffusion equation. This is the diffusion term and this is the advection term, and get the distribution of the solute at any time. Now, to see the investigate the how the solute is transported. So, suppose we consider a portion of the channel. So, in the inlet we are injecting the solute with a fixed concentration, say, which we call as a C reference, which is the scale for the solute concentration. So, that means the non-dimensional concentration is defined equal C equal to, say, some C bar equal to C by C reference, and the boundary conditions are governed by no mass flask on the channel walls. So, that is nothing but here channel walls we are taking as normal is y axis. So, that is the y equal to 0 and y equal to 1. So, what we can impose the condition is del C del y equal to 0 on the channel walls, and the outlet we can have a symmetry. So, that means the symmetric distribution. So, we can have the gradient or fully developed situation for the solute distribution. So, we can have the gradient del C del x equal to 0 of the solute at the outlet. So, this is a elliptic portion of this equation, and also we have the this is a parabolic situation. Hyperabolic we won't say because u is known. So, and this because of the presence of this term. So, if we have this PES is quite large, so that means we have the diffusivity terms is negligible, but that will not be the case for this situation. PES is always of order 1. So, that means it is a kind of elliptic and parabolic combination. So, since it is having a second derivative of C, so we need to know all the 4 boundary conditions and also a initial condition. So, if I assume that initially there was no solute, C is 0 within the channel. And now if we solve, we get the distribution of the solute with time is governed by this equation. So here we have taken the external electric field, applied electric field as 10 to the power 5 volt per meter, height of the channel as 50 2h is 100 nanometer, Debye length as 8 nanometer, and zeta is 25 nanometer. Now we have taken the diffusivity of the solute in such a way that Smith number, this is the Smith number, is given by this way. So the Peclet number comes to be 3.54 because the average bulk flow is which determines the Reynolds number. So this is 10 to the power -3, but Peclet number comes to be 3.54. Now this distribution shows that the solute transfer is mostly occurring through the diffusion mechanism. So see, initially we are injecting the solute, this red are the high concentration, so injecting the solute at the inlet, and it is transporting along this x direction by the electroosmotic flow and by the molecular diffusion. So with time, this is the, so what I find from these results, that the solute mixing in the EOF in the microchannel is very slow process, and it is mostly diffusion dominated mechanisms. So this is the bottleneck of some situations where we need a rapid mixing of the solute, maybe charged or uncharged species. So we need to consider how to enhance the mixing of the solute. So that I will continue with the, so next thing we will continue in the next lecture.